Okay, so yeah, the talk is about clustering and unmixing in the phasor space. It's kind of divided into two halves. I think Lionel has been talking about the unmixing part a bit, or giving some applications. I'll start with the clustering, which is kind of a separate issue, but it'll make sense to you all regarding like further analysis in the phasor space. So clustering, for those who don't know, is one of the machine learning families of algorithms that deals with the problem of given some data. Can you see my mouse on the screen? Do I point? Well, there's no feedback. So if you have some data on a, in this case, two-dimensional space, which is the phasor space, and you have a bunch of points there, the idea is, can we find a way to automatically label these points into groups? No, in this case, the color marks the group. This is group 1, 2, and 3. So this is a very general problem with hundreds of or thousands of applications in all kinds of fields. But in our case, we're dealing with the phasor space, which is this method we use in fluorescence microscopy that maps the fluorescence spectra or lifetime. So the photon distribution along some dimension at each pixel into the phasor plot, so that each pixel here corresponds to a point on here. And then it makes sense that to find an automatic way in which you can select groups in the phasor space to then go back to the original image and see what these groups correspond to, you know? This has been done for many years, and traditionally it's been done manually. You know, people would look at the phasor space and the phasor plot and say, okay, this looks like it could correspond to, in this case, the nuclei on the left side, or this correspond to the cytoplasm. But in the advent of modern technologies, it makes sense to find a way to do this automatically, fast, in a batch processing way. So for that, we did some work with Enrico at the LFD and Belen also from close to you guys, in which this is all simulations. We concocted a bunch of different possible distributions on the phasor plot and test them against the battery of methods out there in the literature. This would be what we call the easy case, in which you have clear separate populations. This is a skewed case in which is the same three populations with a fourth component pulling them down. A case in which we call it size, but basically what you have is that one of the distributions is, say, very noisy. So each pixel has, instead of having a smooth decayed or smooth spectra, it has some less photons. Therefore, it's kind of less accurate, the position on the phasor plot. So it broadens it out. Or different number of points. So you have many points in two of them, and then you have a few of the other. And then the hard case, which is the pulling is mixed all over. This is kind of to test the different ranks of possibilities, right? And then we grabbed all these algorithms from the literature. Some of you may recognize some of these, k-means, k-medioids. These are based on distances. These try to minimize the distance between elements in a group while maximizing the distance between the mean position of each group. There's others based on connectivity and graph theory, others based on density, kind of finding local groups of density and assuming that if the density is constant, that's a single group. Then there's like an eigenvalue decomposition method that is come to fame in the last years. And then Gaussian mixture models, which is the one that we put in the end because it's the one we were aiming to prove that it's the best, which is based on modeling Gaussians on top of your data. This index is the Jacquard index. It reports how well the clustering matches to the ground truth, which is known in this case because it's concocted data. We tested all of these, and you see that some of them start to fail here and there. For example, those that are based on distance to the center of the group, well, these tails start to fail because they are assigned incorrectly to the group that is closest, the center is closest. You see how some methods find outliers in the data, and you can test them all. See how when the group spreads out, the density method fails, and so on. I have marked here the best in each case, and as you see, consistently, Gaussian mixture models on the far right is the one that outperforms the rest, or at least is at the top in each case. So this is the method that we showed that is the best in order to model phasor data. And so let me tell you a bit more how this method works. So at the end, the only assumption is that you can model your data points by a weighted contribution of two-dimensional Gaussian distributions. So it's however many clusters you have, K clusters, the data should be modeled by a sum of K Gaussian functions, each with its own weight or a fraction, where the Gaussian function has this complex expression, which at the end is exponential of a negative position squared. Since it's 2D, it's not x squared, it's a vector times a matrix times a vector, but it's x to the square. At the end, this function tries to model what the equivalent of the one-dimensional Gaussian in a two-dimensional. So you have your data spread out here, and if you project against each direction, this is a Gaussian. You're trying to find a model that describes this. So the parameters are the weights of the Gaussians, however many weights you have, one for each Gaussian. The centroids, the vector that takes you to the center of each Gaussian. The covariance matrix, which is the one that this matrix that describes how it spreads out in each direction. So it's like the standard deviation of sigma in each direction. The matrix is composed, describes the variance in each direction and the combined of the two. And then there's a bunch of algorithms in the literature that have been using similar methods from Pearson back in the 1800s even. And the method that is used to find the best fit on your data has been traditionally the expectation maximization algorithm, which is you start with some random numbers, you assign random numbers to all these parameters, and then try to basically loops until convergence, modeling your data until it fits best your data. It's an algorithm from the 1970s. Let me show you how it operates on actual data. So you see you have an easy case where you can immediately tell these are three groups. You throw the data at random, you have single Gaussian across, and with each iteration, it kind of converges to a final set in which the parameters are no longer changing. Therefore, you can assume that you have found your best fit. Then you can go back and see how well it matches the ground truth. In this case, it's perfect. Let me show you a hard case in which data seems to be all muddled up. And again, you throw the model for three Gaussians, and you kind of recover this, in which you then go back to the original image or the original data and compare it. A nice detail here is that this Gaussian mixture model, what it allows you is not only to model the data with a number of Gaussians, it also allows you to then go back and for each point in your data, find what is the probability of it being assigned to one or the other Gaussians. As an example, say this point on the far right has a total probability of belonging to the rightmost cluster and zero probability to the other two. But some of the points in here, which we have painted in these kind of half, yellow and purple, this point on this side here has a higher probability of belonging to the yellow cluster than it belonging to the middle cluster. So the one on the right and the one on the middle. This can be used then in our real life problems to maybe discard some points, or give it or consider it as a mixture of populations, or whatever it is. This is real data. This is the data that started us questioning these problems. Can we do this automatically? It is a collaboration that started off with a group here at UCI. Tambu was my collaborator for like 4 years working on this project. And what they were doing was labeling mRNA transcripts with combinations of fluorophores. And this is a case in which we were labeling, as a little, just as a little point. Now, let me point out this, that each pixel in an image has a position on the phasor plot. So you have, say, 256 by 256, that's 65,000 points on an image, each on the one spot on the phasor plot. What you're used to seeing is a discretization of it. It's like a 2D histogram of this space in which you compose a heat map. So you're counting how many points fall on each little square. But in reality, we want to work with the actual data, the 65,000 points in your image. Yeah, so I was saying you have they were labeling mRNA transcripts with two different probes. So you have two genes, one labeled with Alexa 647 and the other one with ATO 647. These are two fluorophores that emit in the red region of the spectrum, but have distinct lifetimes. In fact, it's a lifetime of 1 and 2 something, or close to 1 and 2 something nanoseconds. And this is the data we're acquiring for this image. You kind of see two populations here. We tested the Gaussian mixture model, and clearly you see the two populations are resolved. You have a weird intersection area where you may want to discard those points, and then you go back to the original image, and there you have it. You have now pinpointed which of the transcripts correspond to one of the genes and which to the other. This led to a whole lot of work using lifetime and spectra to separate populations in mRNA transcripts. And then as a proof of concept, this is another example that I can show you. Experiment that we did here at the LFD, in which we kind of prepared this group of cells, labeling with 3 fluorophores or dyes that emit also in the red area of the spectrum. This is a single image collected in the 660 to 700 nanometer spectral window. You have lyso tracker, which would label the lysosomes, membrane dye, and then this ethidium bromide, which supposed to attach to the nuclei. This is the lifetime phasor plot of this image. The system detects 3 clusters, and you go back to the original image, and clearly you identify each of these with what you would expect to find. And finally, last example is the continuation of the mRNA transcript work, in which this is a bit of a more complex situation, in which not only are we using 2 different fluorophores to label 2 different targets, we are actually using also combinatorial labeling. So you have an mRNA target with tails of one fluorophore, another mRNA target with tails of the other, and then a third mRNA target, which is labeled with a combination. So sequentially one or the other fluorophore. So what you expect to find is the pure location on the phasor plot for one fluorophore, the pure location on the other, and the one that has exactly 50% of each in the middle. The real data showed up as these 3 clusters, which, as you see, the Gaussian mixture model resolves it, and you can go back to the original image and locate each one of these transcripts. So here it is. Here, so I was wrong before. ATO 647, lifetime of 3.5 nanoseconds. There's a couple of slides here on the limitations of this method. The first one is the linear combinations cannot be modeled. So you can only model data that is the pure emission of one probe or another. If you have regions on the phasor plot that correspond to increasing contribution of a different fluorophore or decreasing of another, you will find these streaks, which we call them linear combinations. So these pixels here correspond to pixels that contain a bit of this guy and a bit of this guy, and there's increasingly more of one or the other. This cannot really be modeled with a Gaussian. This is not a Gaussian. So when you have a single population that is spread out due to noise, that can be modeled by a Gaussian because noise is described as a Gaussian. But in this case, you cannot do that. So you get weird stuff like this, in which the model is trying to account for these linear combinations, but it is actually incorrect. It is not an intrinsic cluster by itself. If you look at the original the data, realize that this is simply the transition between one region and the other. So this is a limitation that needs to be taken into account. And yeah, so clearly linear combinations cannot be modeled. And the other one is choosing the number of clusters. This has been a problem since the very beginning. People are still working on this. It's hard to find an automatic way to figure out the number of clusters. So when it's very easy like this, you can all tell it's 3 clusters. But I could argue that the best model for this data isn't 3 clusters. It is actually a model in which you have 1 cluster for each point. If you stick 1 Gaussian on top of each point, that would be a perfect model. So the computer will, it doesn't distinguish that concept. So some people have tried to come up with mechanisms to penalize the number of clusters, so that the system tries to model the best fit while keeping the number of clusters really low. And then, so these numbers will kind of give you a minimum, which is supposed to give you a minimum where the right number of clusters is, in this case 3. But with the real data, this kind of, you never really get these minimums. You tend to, what at the end people do is find an angle, so somewhere which, you know, the derivative has a sharp edge, that would be the right number of clusters. At the end, in our case, we're doing, you know, we're labeling our experiments with fluorophores. We know what we expect to find. We found that in the mRNA transcript work, we would always allow for an extra group, which would be background stuff, autofluorescence, whatever the sample has that we do not really know what it is. And that will be the group that would group everything that is out there. But yeah, so this is kind of the first part. And now there's a second part on the multi-component on high harmonics. I don't know if there's any questions on the clustering. We can make a little stop here. And if not, I'll just head out. So yeah, this is a more of now a in-depth explanation on, I think, the methods that Lionel might have mentioned before. So as a little introduction, and mixing, the concept of a mixing is that you may have a number of components that are contributing to your measured data. And the question is, can you separate those components, figure out how much of each is present in your sample? So as an example, you may have in a single pixel or in a single measurement, 3 components, each with their different spectra. But what you measure is some combination of that. Your measurement, M here, is the sum of the contributions of each of your components. This would be in spectra. In lifetime, you can think of it the same way, maybe a bit harder to see it, but the idea is the same. You have 3 components that all are excited at the same point. So the 3 overlap here, and then they kind of decay at their own rhythms. You have a fast decay, an intermediate, and a slow decay. And what you're measuring is the combination of the 3 of them. You have, you know, the fast decay in the middle, some slower here, and the tail, which corresponds to the slow decay. And mixing is simply trying to figure out what these fractions are that the sum of each of them give you the measurement. In this case, component 1 for the spectra is low. This will be perhaps 10%. This will be 60%, and maybe this guy would be a 30%. These percentages, usually in over unity, can we figure out these fractions? No. So typically, this is done. The best known method is called linear unmixing, in which you go point by point in your. So if this is discretized in a number of points, each of these points has to be a linear combination of the 3 components. So the fraction times the yellow, the fraction times the green, the fraction times the blue would give to the red. And you do that for each of them. So you have one equation for each of your points here. So it leads to highly overdetermined systems with many, many equations, however many points you have, or bins in the spectral window. And that's a system to solve. The work we did was using the same idea, but on the phasor space, which leads to less equations, and it has some differences, as you will see now. Now, I'm not sure if this is overkill now. You probably have just had a talk on phasor. I may just reiterate in my own words the basic concepts required for this. So as a reminder, you have a list of photon arrival times, which is your measurement, the arrival time after each pulse for lifetime imaging, or the list of photon wavelengths for if it's a spectral measurement. Then each of those photons goes into a photon histogram, which accounts for how many photons are in each temporal bin. So this would be the time between two laser stimulations, or it will be your spectral window, and this will be your wavelength, the spectral curve of the emission of your sample. The phasor transform, what it does is grabs this function, intensity over time or intensity over wavelength, and transforms it to the phasor space by computing these 2 numbers. It is a integral of the intensity times a sine function for the s coordinate, normalized to the actual function, and then the same for the cosine. These integrals, all they do is kind of capture the shape of your decay or your spectra, and the key point is that because they're normalized by the intensity is independent on the height or the how many photons you have. It's not completely true because if you have very few photons, this is going to be very jagged and the position will be less well pinpointed. But let me show you here a little animation of what this operation would mean graphically. So you have your decay over time, which is intensity over time. You stick a sine function that fits exactly in this stimulation period. This would be the product of the two. You multiply these two functions. The area under the curve is your integral, and this area is a number that goes to the phasor plot, and that's your vertical coordinate. You do the same with the cosine function, product, the integral, and its some coordinate, and that would be the phasor coordinate of this decay under this phasor transform. Now, I'm going through this because if you notice, I fit the sine and cosine function once in the window. But here you can not only fit it once, you can fit it 2 times, 3 times, and more times. This is a harmonic number, so it's what so tracking back. The phasor transform at the end is the first 2 elements of the Fourier series that describes that data. But the Fourier series is a composition of higher and higher harmonics. So it's like the simplest description of this shape. But you can use higher harmonics to capture, say, double bumps, or at the end, if you use very high harmonics, you will capture all the noise. So as an example, I gave you here for n equals 1, you're fitting 1 period of the sine and cosine functions. But what happens if you fit 2 periods? Well, you're going to capture different quantities, different shapes, and the same decay was going to fall into a different position on the phasor plot. High harmonics, so on. As you notice, the same decay is giving you a different location on the phasor plot. This is one key point that I'm going to use later to explain the high harmonic separation. Other key points that you've probably heard in the talk before. If you assume that your intensity as a function of time for a lifetime decay is described by a decaying exponential, so you have some number tau here, which is your lifetime. If you plug this expression into these 2 integrals and solve the integrals, what you obtain is the equation of the universal circle, which is telling you that only and always, every time that you have a pure exponential, your phasor position is going to be on this circle. And in fact, you see that when your tau is a small number, you're on the right side, and when it's a big number, you're on the left side, right? So this is short, and it goes increasingly. This is highly nonlinear. It's kind of very crowded here. This is 0, goes up to some number, and then it goes up to infinity here. And any combination, which is no longer a single exponential, it's some combination of exponentials, will fall inside this circle. The other key point is that phasor addition follows linear algebra. So the rule of the linear combination. If you have 2 components that are mixed in one same measurement, the linear combination of these 2 positions will give you the position of your measurement. So if you have exactly 1/2 of the photons is coming from one component and the other half from the other, then your measurement is going to fall exactly in the middle. So the G coordinate of one component halved and the G coordinate of the other component halved is going to take you to the G coordinate of your measurement, and the same applies to the S coordinates. And this follows for any linear combination of your components. Finally, that higher harmonics of pure components, but only if you are on the universal circle, can be computed analytically. This is an expression to relate the higher harmonics coordinates to the first or any harmonic. That is not true for anything that is inside. So linear combinations you cannot find the higher harmonics analytically. Okay, so all of this to set you up for the actual multi-harmonic unmixing. So if you have a 2-component problem, as I was explaining a moment ago, you have some measurement, this point in the middle, the capital G and S, this is your measured data, and you know that your measured data is composed of 2 components that are present in your sample. Then you can solve the system of equations on the phasor plot if you know the position of the pure components. because as I was saying, you know that there's a linear combination for the G coordinate, there's a linear combination for the S, and you know that the weights should add up to unity. So you have three equations, only two unknowns, which are the weights of the two components. So this can be solved. Three equations, two unknowns over determined system. In the three-component problem, that is the determined system with exactly three knowns and three equations. Thing is, if you have a four-component problem, so if your data point, there is four components, lifetime components or spectral components in there, this is an undetermined system. You have more unknowns than equations. You can only write an equation for G, one for S, and then the fact that each of the fractions add up to unity, but this cannot be solved. There's 0 to infinite solutions here. So here's when the higher harmonic comes in. If you compute the second harmonic of your data point, and you compute the second harmonic of your pure components, you get a new polygon here. This is your original measurement. This is the second harmonic of your measurement. And then you have the second harmonic of the pure components out here. This gives you a new pair of equations. So you have now two new equations for the second harmonic. Therefore, you have now the tools to solve this problem because you have four unknowns and five equations. The system also, this data is always going to be noisy. It's not going to be perfect, so it's not a perfect solution. Typically, we resolve this by least squares, so you find the best combination of weights that satisfies all the equations. Remembering the key point number 3, that you can relate the higher harmonics S and G of the pure components to the first harmonic. Okay, so this led to work with Lionel and other people at the LFD, in which we were using this to unmix both in lifetime and in spectral data. This is one of the first data sets that we used. We were labeling with 4 components and attempting to find, say, in each pixel of the image, what is the fraction of the known 4 components in that pixel? As you see, the polygon here is not even on the phasor plot, on the universal circle, because what we did is, knowing that there's probably other components in the experiment, which autofluorescence and so on, we went and measured each of them. So we prepared a culture with only one of the dyes, then the other one, then the third and the fourth, measured separately to find the locations of these dyes on the, say, contaminated phasor plot, and then did the measurement with the 4 of them together in order to find what is the proportion of each of these components in each pixel. And a very similar experiment, I think this is data that Lionel may have shown to you in the previous talk. This is work in collaboration with the group here in Uruguay, in which they were labeling, this is Laurdan, which is, it's a single dye, but it's actually 2 components corresponding to the relaxed and non-relaxed. And then there was 2 other components, and the same idea. You have a single measurement here, and it's nice to see how, for example, you can now, the unmixing has given a high fraction for, say, the mitochondria that you can start to see, or you can start to see the membranes in the 4th component. And the work, what we did is actually use the unmixing to then separate the contribution of the other 2 dyes to go back and have just a pure proportion of the mixed versus relaxed versus non-relaxed Laurdan. Finally, this is kind of a slide that wraps up. This is a graphical interpretation of this higher harmonic, how it's solving the problem. Let me walk you through it. You have this is all conceptual. Say you have 5 spectral emissions, each of them just very distinct. No, you have these 5 pure components, and then you prepare 2 mixtures of these components. For example, the first mixture corresponds to half of pure component 2 plus half of pure component 4, which would give you this double peaked spectra. And then you have another mixture, which is a combination of the other 3, such that there is equal proportion of the first and the fifth and some number, so that you get this triple peak here. You can find a number phi such that these 2 completely different spectra, the one with the double peak and the one with the triple peak, go back to the phasor plot on the exact same position. Here's the ambiguity of the phasor. This is the reason why on the first harmonic, if you have a measurement here, there's no way for you to know if this measurement is a linear combination of component 2 and 4 or 1, 5, and 3, and any other combination of these four. This is the ambiguity that if you go to the second harmonic and you map these same two spectra, you realize that now you have resolved the ambiguity, because one of them maps to the linear combination of 2 and 4, the other one maps to the linear combination of the other three. So in the work we did, we compared this to traditional linear mixing, and we showed that it is known that linear mixing fails when one of the components dominates over the other. So when there's a high fraction of one component, we show that phasor multi-harmonic unmixing is kind of dominate, or is better than traditional linear unmixing. So here's kind of a distribution of as the number of photons increase at the end. If you have enough photons, it is easy. The error is super low, but conditions in which we usually operate this is photons per pixel. So we're talking about a few dozen. So we usually operate in this region in fluorescence microscopy. So from a few photons to, say, up 100 per pixel. And we showed that after a certain fraction, it is better to use the phasor unmixing. In lower fractions, so this can be it should be used as a combination of methods. No, so you can use both methods and use kind of the mix match of the two. And then as a final part of the talk, after doing this work at the LFD, I remember kind of naively going into Enrico's office and saying, hey, if we're adding more and more harmonics and we're finding more and more knowns there, can we just simply add infinite harmonics? Can we just add to find infinite unknowns? And he said, definitely not, because look at how the data is spread out. As you add harmonics, the positive and the negative sign of your transform is kind of compensating each other, and at the end, all the harmonics go to 0, and your data. So this is kind of the first. These harmonics are all joining up to 0, 0 coordinate, and at the end they're all together there. But what is true is that using high harmonics, we may be able to find the fractions and the lifetimes of a small number of harmonics, which is what Leonel referred to as the blind unmixing. So till now, we knew what components we have in our sample, and we were trying to find the fractions of each of them. But we showed that you can actually also find the lifetimes of these. So if for a very small number of components that you don't know what is present, you may be able to find not only the fraction and the lifetime. This is a kind of math-intensive slide, but the reasoning behind all of this is the combination of these concepts. We know that there's a universal circle, so that S's can be expressed as a term of G. We know that the higher harmonics, as I showed before, can be expressed in terms of the lower harmonics. Yeah, these are not exponents. These are represent harmonics. And an example for 3 components, you would have 6 unknowns, which is the G's of the 3 pure components, the S's of the 3 pure components, and the fractions that we were searching in the previous case in which we knew these guys. So if we now don't know these guys, we have a bunch of new unknowns. Using the relationship in the phasor plot, we can relate all the S's in terms of G's, so we reduce it to 6 unknowns. So that means we need 6 equations to solve for these unknowns, requiring at least 3 harmonics, which would give us 6 + 1 equations, as I showed you before. So you have the sum of the G's, gives you the capital G in the first harmonic, the same for S's, same for second harmonic, and so on. And then the sum of fractions should add up to unity. This is a set of nonlinear equations now, because these are products between components. This is a mess here. The only way to really solve it is by doing a kind of joining all these equations, coming up with this number, trying to minimize this number, and then going into some higher dimensional space and solving this minimization problem. And we show that it's kind of hard to really solve these problems, because usually there is a set of what we call the valley of solutions, but sometimes you can find the true solution. Here's an example we prepared with 3 nuclidides. And this method solved for each pixel in the image gave us these three distributions where the peak position kind of matches the expected lifetimes. So we showed this for different cases. And then we applied it also to a set of data that was being used at that time, in which you were feeding mice with low fat and high fat or Western diet. These are images of livers of mice with completely different fat content. And we reproduced a previously known data that fat introduces a long lifetime species, which our method was capable of detecting and pinpointing. And yeah, and we showed that then you could use the same method to go kind of remove this long lifetime, and then go back and compute the ratio between the other components present in the sample. So yeah, that's the end of the talk. I would like to acknowledge the LFD family, especially Enrico, Michelle, and all the people that worked with me before and after leaving, and of course Lionel for holding the workshop. Thanks.